Welcome back to Digital System Implementation. This is Chapter 5, and it's basically CMOS performance issues. So, as you probably know, the basic performance criteria for VLSI or ASIC design typically is more and more speed, but at the same time you may have to worry about power dissipation because it could become a big issue. With respect to power dissipation, it breaks down into two families: dynamic power dissipation, and that's associated with the frequency of operation, and static, which is associated with leakage currents. Performance degradation may result from many factors, and some of these can be minimized through device design, as well as perhaps making the circuit synthesized differently. And basically the rule of thumb there is that, some of that's within your design, within the designer's control, and there's more than one way to skin a cat. Some of the performance issues, you may have thought that CMOS might have a relatively large fan out, but that's only true if you really don't care about the clock speed. If a toggle rate or clock speed is specified, then CMOS can actually have very poor fan out. So it's this type of performance issue that we'll be looking at in a fair bit of detail in this chapter. Some of the performance issues here we're going to look at when it comes to limited fan out. Maybe you can still design the circuit, but even with that limited fan out, the design may still be too slow, and that could have been a consequence of a long interconnect line, which contribute to performance degradation. So in this chapter we'll look at some basic modeling. We'll take a look at long lines and initially just look at them as lumped elements. We just sort of basically calculate how much resistance and capacitance is associated with them, and then we might move on to a distributed RC section, which looks more like a fusion model. In the next section we'll actually look at transmission lines. An improved design may require more drive. Well, as a designer, you know that the drain current is proportional W over L, and you do as a designer have some control over the widths of transistors. Alternatively, you may cascade increasingly more powerful high drive devices, in which case you might be driving a large external capacitive load, and you'll have to basically amplify the signal. For specific applications, it might be economically feasible to consider, although very unlikely, some kind of mixed technology, which might be a bi-CMOS or something, which would give you the benefit of a high-speed bipolar with the logic of the CMOS, but as I said, that's pretty unlikely. The following calculations are rough estimates, and they're the basic aids to understanding of CMOS device operation, not intended to replace more detailed simulation such as HSPICE or device circuit simulation. Some of the performance issues are related to switching, and what we mean by that is we need to define a rise time and a fall time. So a fall time is, as you might imagine, the signal falling from a high output level to a low output level, and a rise time is rising from a low to a high. These values are somewhat arbitrary, placed at 90% and 10%, because you'll see from our simple models, if we didn't do something like that, we're going to basically have RC type time constants, and as a consequence you'd actually never have a number that you could associate with the fall or the rise time if you strictly went to the 100% levels of VDD and ground. This is sort of schematically what we're looking at. Again, there's the figure for the rise and fall times. Happens to be our simple inverter gate again, and typically what we do is we try to estimate the performance of this gate. So what we do is we basically take a look at what the output is talking to. In this case, we almost always assume it's talking to an identical gate, and as a consequence, this output gate that we're talking to ends up getting modeled as something like this. So we basically have a capacitor with the bottom plate on VDD and another capacitor which is the bottom plate on ground, and it represents these two gates that you're actually talking to here, the physical CMOS gates of the PMOS and NMOS transistor. That thing gets modeled as the output capacitor, which is simply just the sum of C1 and C2. And that whole thing is sort of modeled from the input of the actual gate that we're trying to estimate the performance of. So it may seem a bit peculiar to do that, but it's really just one gate talking to a very similar gate. So one simply uses the same gate or layout to estimate perhaps what the capacitive load might be for driving a very similar gate, and that's just a convenience to make it a little easier to maybe estimate what the capacitance is. So it might seem a little funny that the load capacitance is calculated from the same gate that is doing the driving, but that's typically the way it's done, and in the assignment or two we'll have, I'm sure a few of you will get that wrong, but once you get done it once you do it Once wrong, you'll get it right after that. The switching issues are always related, or typically always related, to capacitance and obviously resistance as well. But the load is almost always capacitive, and that's because you're talking to the PMOS and NMOS channel gates of another inverter or another gate, and these are MOS capacitors, metal oxide semiconductor capacitors. The interconnects are also capacitors. They're metal, running on top of a thick dielectric, and these are parasitic capacitances, and they're in parallel. Therefore, they combine additively. So that's the thing to keep in mind. These capacitors are added together. The bottom plate of a capacitor of the P well is over ground. The bottom plate of the capacitor over the N well is over VDD. But this doesn't matter because these two voltages don't change. They're stationary or static. Anyway, we can go and take a look at our current equation. It might be given as this, and this is just the total current flowing, let's say, out of that gate I1 plus I2, where I1 is going onto the NMOS MOS capacitor, I2 is going onto the PMOS capacitor, and this is C dVdt. So it's just these two terms here, and we know that VDD is a constant, so it basically drops out of that differential, and we're just left with C1 plus C2 as we'd established before. And in any event, the effect of the capacitor is additive, and the way to think of that, it's always a bigger load. And the bigger the capacitance you have to drive, the slower the device is going to be. The capacitors are charged and discharged through the NMOS or PMOS transistors of the inverter. That's the only way for charge to get on capacitors. And these MOSFETs have non-zero on resistance. We saw that earlier on when we looked at the ID, VD characteristics of those devices, and that's the R that contributes directly to the RC delay. And you might want to go back and take a look at what the ID versus VDS characteristics look like, and you'll see it sort of did resemble a resistor in the linear region. So the principal limitation of switching speed is charging and discharging of a load capacitor through a device resistance. And that leads us to the first in-class assignment for this chapter, and that question is, what is the principal limitation in switching the speed of a CMOS gate? You shall be able to answer that in a relatively short time. And we'll be back shortly.